Can I just say, this is probably the most professional conference I've been to in a while, and it's a B-Sides organized by Martin. That's amazing. Can I just say, it's so cool. Even the badges that you guys are wearing, I think they're amazingly well done. So thank you so much for the opportunity to be on your inaugural conference, the first speaker. It's an honor that I very much appreciate. Thank you. While I don't fuck it up, let's actually talk about what I'm here to tell you about today, which is, let's see. It's the infamous clicker. There we go. So what I'm here to talk to you about is how we can have a secure quantum future. And you might think like, oh my God, really? We're going to talk about quantum? Yeah, we really are. Because what I hate that we do together collectively is we don't prioritize things that are important until they become bloody urgent. So we're going to talk about something that isn't urgent yet for some people, but maybe it should be. So I'm just going to keep trying to click very stubbornly. So what you should know is that in Europe, we have a quantum flagship. And it's a quantum flagship that means that there's €1 billion reserved for all things quantum. €1 billion. The EU doesn't do that often. The only times they've done it before is when they tried to study the human brain, which is kind of hard, and when they tried to figure out what the hell to do with graphene. So of all of the flagships, there's only 3. The brain, graphene, and quantum. And what they're trying to figure out is how do we, crack this nut of this quantum stuff to keep intellectual property and prosperity for Europe. They think it's so important and so fundamental that that's why they're putting €1 billion of EU money in it, in light of everything else. And if we go to the next slide, what I want to tell you about is that, you might think of quantum as a singular, homogeneous thing. It's absolutely not. There is a field around quantum. That's not a physics joke, but there's a field around it, which is really like computing. And then you have quantum communication. You have quantum simulation, and you have sensing and metrology, which is how do we make better clocks? How do we have more precise measurements and sensing tools? If we go to the next slide, all of those pillars, if you will, around this, that's how the flagship is organized. All of those pillars require a whole bunch of other things to happen before we get a quantum computer, before we get a quantum gravitometer, which looks at Earth-specific gravity, or better clocks. You need this area of enabling science as well as theory, algorithms, and protocols. And there's so much work that's being done in each of these pillars. That's why you need a little bit more investment in order to get this stuff off the ground. And if you look at competing countries, they're spending a lot more. So you should know that the goal eventually is to hook all of these different disparate types of technologies together. So hook up the clock with the computer. So making an entirely new backbone for the internet that doesn't just drive our current equipment, but will also be able to connect a quantum computer to it. And that the quantum computers can run fully native on a post-quantum computing network. So we're looking at things that will be terrestrial components, but also space-based. So the European Space Agency has a project already for a few years called Skylight. You can look it up, which is all trying to figure out how to deliver this stuff from space. So if we keep going, one thing I got to tell you, no matter what else you guys do, regardless of what we're trying to say, there's so much other stuff that's broken, shouldn't we fix that first? I've got to tell you that regardless of all of that stuff, there will be a quantum computer. Because the kind of thing that we've enjoyed for the last couple of decades has been Moore's Law. Everybody knows Moore's Law? Anyone not know Moore's Law? All right, so I heard a giggle. That means someone doesn't know it. But they're uncomfortable. So I'm just going to tell you, every 18 months, your computing power doubles. And roughly what we've been seeing is that there's an asymmetric decline in price. So your computing power keeps doubling, boop, 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 every 18 months. But what we're also seeing is the price keeps going down for all of that processing power. And what we're now seeing the emergence of is something called Amdahl's law, which is that you can keep adding stuff, keep adding processing power, but you're actually not getting that additional compute that you originally enjoyed. There's actually a decline of that processing power. So even if we don't really want to, we're going to need quantum computing to answer some very specific problems. And these very specific problems hold a lot of promise. You know, the promise is things like it's going to help us figure out how to do personalized medicine and, you know, do better detection of cancer. You saw that, like, Google's DeepMind is also working on problems like protein folding. These are also problems that a quantum computer is ultimately capable of doing because it can map all of these different scientific interactions. So if we go to the next slide, you got to know that the people who are the most advanced and in terms of pure determination and meeting the bloody roadmap. I have a deep admiration for projects that are delivered on time and what they said they were going to do. It's IBM. Not very sexy. It's IBM. And IBM currently possesses, and you'll see it here, we're at Condor, I believe, at 1,121 qubits. And then, like, we're going towards 1,386 plus qubits. In order for it to be useful, we need millions of qubits. But the expectation is once you have a stable architecture, scaling is going to be how these companies are going to achieve it. But it's not just IBM. It's Google. It's Microsoft. It's everyone and their mother working in an NSA basement. All of these people are working on a quantum computer. And if we go on, you might want to know why. Because there's some cool, funky bits about a quantum computer. First and foremost, they're not the same as what we have. So you might have heard before, it's not bits, it's qubits. Why? Because on a bit, you can write one operation in a way. It can either be on or off, and in this particular example, up or down. And if you think about this property that a quantum computer has of spin, you can think about how this quantum computer can actually be those things at the same time. Instead of just being up or down, on or off, it can be up or down at the same time. So what does this do? That increases your ability to write a particular operation or keep a particular value. Because instead of having one that was this way or this way, you now have two. Okay? And when we look to the next slide, what's really cool is when you have this up or down at the same time hooked up to another up or down at the same time. And when you want to look at, how do quantum computers do that scaling? It's through this property called entanglement, which is that we create this bond in between them. And when things are maximally entangled, they result in a perfect symmetry. When they have this, you basically have to think of every quantum computer you're looking at with the amount of bits, you have to take it 2 to the n, where n is the number of bits. So I'll give you an example. If I have 1 bit and it's 2 to the n, what's 2 to the 1? Come on, guys. I know it's early, but we can do this. 2 to the 1 is 2. If I have 2 qubits, right. So if I have 3 qubits, I know, I heard someone whining, 8! So, but you get the idea. So if I have the biggest supercomputer on Earth, and I want to double it, what do? No, add an entire supercomputer next to it. I have the biggest supercomputer on Earth. If I want to double it, I have to build another supercomputer. And Milan, who always knows my thingies, thank you. Hello, good morning, Milan. However, if I want to double the power of a quantum computer, all I need to do is add 1 qubit. Okay? It's not Moore's law in 18 months. It's Moore's law instant gratification version. Are we all cool? This is why people are so salivating at this notion of creating something like this, because it keeps delivering if you add just 1 more qubit. Okay. There's also another property that I want to mention very specifically. There's this notion of noise. There's stochasticity built into a quantum computer, which means that the least thing can disturb it. It can collapse that quantum state. So there's a degree of fragility baked in to everything quantum. And at the same time, that fragility means that you can't actually copy communication. So TCP replay attacks or, any other type of interruption or interception will actually be noticed by the two parties that are communicating. We'll talk about that a little bit later if we keep going. I want to explain why it's a threat to cryptography. Our current cryptography is based on difficult math problems, okay? Really hard math problems, which we cannot figure out because we need a lot of time and processing power, frankly, to do it. So it's based on very large prime numbers, really large primes that are multiplied together, basically, in a complex operation. And in order to kind of derive what was originally parts of those operations, that's difficult. So that problem is called integer factorization. So I'm going to make it super simple. I'm going to pick on someone in the audience, and I'm so sorry it's you. So what's 9 times 8? Yes, good job. Now, what are all the factors you can multiply together to get 72? That's right. What are they? Don't stall. Yeah. Okay, so what you're doing is really good, but this is what our current computers do. When we ask them to multiply two large prime numbers together to get some secret ciphertext blob, right? I'm oversimplifying, but you get the idea. If I do that this way, the computer goes, oh, the output is blah. That's great. Now you ask our current computers to reverse that one-way function, and it takes a long time. Maybe the lifetime of the universe to reverse. So that's the strength of a one-way function, depends on how much time you need to reverse it. You need time to figure out what all the factors of 72 are. But if I say 9 times 8, we're pretty relatively, even without coffee, quick to answer that. Everybody get this notion? All right. So this is the point. Our current computers cannot do this one-way function for integer factorization, but they can't also do it for discrete logs. So if we have this formula, 3 to the 16th with a modulus, which is just a remainder of 17, you have this answer. Yeah? So this is also known as clock arithmetic, but we have this answer. Now, if we only have the answer, trying to figure out what the hell the formula was that created it becomes also really, really difficult. That notion, I think, is also pretty clear, right? But what happens is if we click down, we have really 2 very cool algorithms. We have Shor's algorithm, which can help us reverse the integer factorization, and we have Love-Grover's algorithm, which allows us to perform different computations in a sort of maze-like thing. If you had a maze and you had to solve it, sometimes you draw a line like 1 by 1, right? What Grover's algorithm allows you to do is test all of those possibilities at the same time. So it's an optimization algorithm. It allows you to try multiple outcomes at the same time and thereby getting the answer quicker. So again, because it's a time-bound constraint, both of these algorithms reverse the time that it takes. Okay? And if we go to the next one, and you guys know, right? I'm not telling you to do quantum at all costs. I'm a chief security officer, and I can tell you our hardware sucks. Our operating system sucks, protocols, applications, if all of those things are vulnerable and shitty and susceptible to backdoors, then it doesn't matter how good your crypto is. The attacker isn't going to attack your crypto. They're going to attack one of the weak underbellies before it. So we need good cryptography, but we also need a really clear understanding of what the hell it is we're trying to protect from whom. Yeah? So don't do this shit before you do that. By the way, you guys want to sit down? There's tons of chairs. Tons. Okay. Standing is good. If we go to the next slide. And you might want to know, when will we have the quantum computer? Well, I already told you that IBM in 2024 isn't going to get there. Okay, we need millions of these suckers. So in order to get to the millions, we're looking at some time. And what you should think about is, remember I told you, we're going to have to do something that's really cool if we want to break things like RSA. If you take a time factor of this, of how long it currently takes to break RSA, which is, again, potentially lifetime of the universe, and if you have a lot of qubits, you'll basically bring that down to a couple of seconds. Again, big problem. And depending on the amount of qubits, you bring down that operation to a couple of seconds. So we need a lot of qubits in order to perform this well. So if we go to the next slide. Martin, sorry. The other issue we have is a capture now, decrypt later problem, which means that everything we've ever transmitted that was encrypted is actually at risk. Because this is a photo of the Utah data center facility of the NSA, where they keep captures of internet traffic. By the way, they're not the only government that does it. Every government captures internet traffic. They also capture the encrypted stuff. And that's because, sometimes old secrets are just as good as new secrets if they have this predictive force, and you can then use them to figure out how other future communications or codes or whatever will be done. So go to the, yeah. And right now, I just want to ask you guys, we don't know all of this other stuff that could potentially be at risk because this stuff is at risk because we use it everywhere. But what you should see is really fundamentally everything we currently use in our modern cryptographic stacks is going to have to be replaced. And even when you have a larger key size, which is absolutely something you should all be doing, even when you do that, there's still a concern around the key management functions to know that they're still really going to be okay for the long haul. So even AES, even with the larger key size, I still worry about key management and how we're doing key management across the board and asset understanding of cryptographic algorithms, because most companies don't have that. If we go to the next slide. So when you're trying to figure out, like, what should I do? I think first and foremost, you need to understand how long do I need to keep my current cryptographic stuff, the stuff that I encrypt, how long do I need to keep it secure? Any ideas? How long do you guys keep your cryptography secure? Forever. We don't know how to do forever. How about we say, like, 23andMe data? How long would you want that secure? Are we going to go back to forever? Yeah, even that we don't know how to do. Or maybe even the lifetime of you and your children, we don't know how to do that yet. So it's a real challenge. Like, I think healthcare data, which is also the most often vulnerable to these types of attacks, because you can change your credit card, can't really change too much about your medical stuff. I think this is really a fundamental problem. So the healthcare industry has a huge issue, but so does the banking industry, who also have long-term secrecy needs. So let's say they want to keep it secure for 20 years. Okay? 20 years, we'll buy that. That's like a reasonable interim. So let's say we need to keep it secure for 20 years. How long before there's a viable quantum computer that breaks our secrets? So I talk to folks that are building quantum computers pretty frequently. And I can tell you that the least optimistic ones say 10 years. The more optimistic ones believe that there might be one somewhere, because there's always scientists that come to these conferences that don't show any papers, that are always there. Anyway, so there's all kinds of theories about when there's a viable quantum computer, but I really would be more hesitant to be more optimistic. I'd rather be more pessimistic. So let's say that before there's one in the public domain, we need about 10 years. There's also quantum skeptics, which say that you'll have cold fusion before you have a quantum computer. So how long do we need to work to transition our network and systems to something that's quantum safe? Any ideas? Yeah, because we're so good at, like, IPv6 transition. That's my litmus mark. So, no, look, but genuinely, we're not good with change, and we're not good with upgrading things that we know need to be fixed, because unless there is an urgency attached to it, we rarely do anything. So I really think that if we say we need to keep stuff for 20 years secure, but there's 10 years before there's a quantum computer, we've already got a problem. And then we need another decade to transition, then we still have a problem. So we have a massive problem. We should have started, a decade ago, basically. And if we go to the next slide, I think what we need to do, first and foremost, I'm going to be really pragmatic and super simple. First and foremost, figure out what cryptography you use and use the maximum key length wherever possible. Then look for opportunities in very tiny specific areas for something called quantum key distribution. I'll explain what that is. And then finally, look for what I believe is the most stable long-term solution, which is post-quantum algorithm. Jakob Krustek, hey. And then if we go to the next slide, yeah. So I'm going to explain what QK. Sorry, it's really hard to do this when there's, like, only friends in the audience. So what I wanted to do is explain to you how quantum key distribution works, which is basically you have two parties, Alice and Bob, and then you have Bob's jealous ex-girlfriend, Eve. All right? And so Eve basically wants to know what Alice and Bob are DMing to each other. And the clue is, what did I tell you about interception? Anyone remember? It's not happening. Yeah. So if we go to the next slide, the way that it really works is QKD prevents Eve intercepting without Alice and Bob knowing. That's it. That's all you got to remember about quantum key distribution. Because while you're distributing the keys, you want to know that the channel is secure. Yeah? So it's a key distribution issue. And the way that it really works is you have a little box which has a bunch of polarizers, diagonal and horizontal. There's a single photon emitter on this side, which is your photon source. It emits a particle of light. when the polarizers are oriented in a particular way, the light passes. If they're oriented in another way, just like a regular polarizer, you guys have polarized sunglasses, right? Do you know how if you tilt the angle by 90 degrees, you don't let light pass? Yep. It's the same thing. So light passes or it doesn't pass. So when the light doesn't pass, and, Bob's polarizers aren't configured to receive Alice's photons, they know Eve has been hanging out in the middle, because then Bob gets gibberish. So when Alice's polarizers are set up correctly, with the single photon source working properly, and Bob's are set up correctly, we're cool. If Eve is in the middle, it shifts everything and they get gibberish. Is this idea clear? Okay, cool. And if we go to the next slide, you can do this because there's limitations. When you do this over a fiber channel, like a fiber optic cable, it's really a problem because there's distance limitations. The maximum distance limitation on fiber for doing this kind of stuff right now in the wild, like in a lab you can get up to 120 kilometers, but in the wild you usually get to closer to 9 or 10 kilometers. And sometimes if you're lucky on really good Dow Corning fiber, you can get about 64 kilometers. They've been test done with 64 kilometers. But unfortunately, I don't know about you guys, but I communicate with people that are further than 64 kilometers away. So as a result of which, in order to get a secure connection happening, then we're looking at something called free space QKD. It involves lasers. So we have lasers at very long distances. This was 144 kilometers. This is one of the earliest experiments that was ever done in Europe by Paolo Villarese, an Italian scientist between La Palma and Tenerife. And he managed to do this regardless of the vapor and everything else. It was a really cool experiment. But if we go to the next slide, we're way beyond that experiment phase because China, since 2016, has been operating a space-based QKD communications satellite on top of a terrestrial network. This was the original terrestrial network. It's about 10,000 kilometers long. It's now 3 times as large. So they have a terrestrial QKD network, completely secure against any attack from a quantum computer across all of China, and they have this satellite to go with it. That satellite didn't just prove its capability to have secure communications with China. They did an encrypted video call with the professor of Panjiang in Vienna. What's his name? Thingy. But they did an encrypted video call with him in Austria. So this thing works, is all I'm trying to tell you, and it's worked and it's been operational since 2016. I told you that Europe spends about 1 billion on the European flagship, right? China spends 10 billion. They also have private funding for all of this stuff on top of, the stuff that's in the 5-year plan. They also encourage private companies like Alibaba, etc., to also fund labs, research for quantum. So if we go. Globally, what I believe is a more stable solution for all of us is post-quantum cryptography. And where you look for all of that is NIST. So I work with ETSI, which is, by the way, if you guys are really interested, having a conference on May 14th to the 16th in Singapore on all of the ETSI PQC algorithms in close cooperation with NIST. And what we did is in 2016, there's a call for candidate submissions for all these algorithms and in different categories. And then we're now at the final round where, we've had previous rounds, stuff has been broken and challenged, and now we expect standards to be coming out this year, roughly end of the summer, beginning of fall. There will be standards announced, and there's already actually pre-selected candidates that have already been announced earlier. We'll get to that in the next slide. But here's the thing. How many of you guys have already looked at or played with or examined any of those new algorithms? Wow, you're cool. Okay, so there's one person back there, which we all should meet afterwards. But the idea is not many, and we all need them. And we can't just rip and replace them. So if we go to the next slide. Oh, no, previous one? Sorry. So here's the deal, right? These are the finalists that we have in the round, and we have signature algorithms as well. And then there's alternates. Of those alternates, Psych, for example, you might have heard about it, was already broken, and not with a quantum computer, but a really old computer. The clue is that we need more people testing this stuff, trying it out, breaking it, before we genuinely know that it's secure to use and viable. There's also trade-off constraints in bandwidth, in CPU utilization. So you cannot just take one algorithm out, pop in another, and then hope that we're okay. That's why we need to try them out. And I worry about all the things that can go wrong. Because every time we try to do stuff around cryptography, we know that governments are still interested in figuring out, how to do cryptanalysis. We will still have people like, I have invented a super secret algorithm all by myself. I'm not going to tell NIST or anyone else, and it's super secure. That's going to happen too. So there are governments that do not engage with NIST or with Etsy or anyone else and are actually rolling their own crypto post-quantum. Okay? And no one's testing them up. They're not up for peer review. You should be terrified. And then subsequently, we don't just have cryptanalysis, which is, finding a mathematically orientation for an attack or looking at the traffic and trying to figure out a way to attack. We still have all other kinds of problems around if the entropy source that we use for some of this crypto is good. If, because we've seen that go wrong before with the NSA introduction of weak entropy sources for other algorithms. So I really think that there's so much that can go wrong just purely from a technical side. And if we look from a legal side, we also have these arguments that are there to figure out how to balance equities. Either ban the crypto altogether, no cryptography. You guys might have seen recently there was all these really big issues with iCloud usage and encrypting things in iCloud. Did you guys see that? So there was a parents association, because I think the root password for all of this stuff is if you can say the words terrorism or pedophilia, you can weaken or ban cryptography pretty easily. So those arguments are there to either, also restrict crypto. So the good crypto stays at home and everybody else who uses our stuff gets the weak shit. So we can then decrypt it. Or, France's biggest arguments for key escrow. We'll keep all of the, KI material with us in a super secret vault, and you guys on the mobile network, you don't get anything else. So I think there's all kinds of worries that we have, because when you look at the alternatives for law enforcement, there are things like buying vulnerabilities and cashing in the O-Day market. So I think that we need to come up with better solutions all around, but in the meantime, we need to figure out how to get our crypto up to scratch. So if we go to the next slide. What I want you guys to think about, if there's one thing you leave with after this talk, I want you to think about just one question. What cryptography do I currently use? So the Biden administration in 2022 already said that everybody needed to figure that out from a government capacity to understand their own cryptographic assets. Assets that we regularly do in a CMDB or asset inventory, they need to include cryptography. So that's the first thing. Then we need to think about how are we going to implement this stuff. I'll talk about that later. Make policies, which is super unsexy, I know. And then also talk about the vendors that we use across the thing and which crypto they use, because that's just as important, because finally that's what you use. And make sure you have this stuff in very unsexy contractual annexes supported by legal, and make sure you break stuff quickly rather than finding out at the 11th hour. So there's this roadmap. I'll happily share this with anyone. I presented this at RSA. There's this roadmap for readiness, which basically says you should have started last year, which is very similar to what the Biden administration did. And then have this a phased approach where you're discovering, and then you're implementing things, you're breaking stuff, and then you do this monitoring backup phase. Because the name of the game is cryptographic agility. Assume that any algorithm you choose will break. You will need to replace that algorithm with another candidate algorithm. So you need to not just pick one, but have two. Cryptographic agility is the only way that we can handle when stuff breaks and that we then can replace it. So if we go to the next slide. The other thing too is, and I'm going to keep this super simple, we need to be able to evaluate threats. There's a lot of information and disinformation out there. So trying to understand, what the different side channel attacks are, that's not what I'm going to ask you to do. But I'm going to ask you to, very carefully select the sources of information that you choose to look at without delving into the rabbit holes that are somehow out there, online. It is really quite a lot of stuff. And I think that really, if you select your sources carefully, then you'll be in much better shape for evaluating threats. The other thing, too, is you can start taking existing products that are already there and just start playing with them. Just start experimenting with them. So there's VPNs that already use post-quantum cryptographic algorithms. There's OpenSSH. There's post-quantum chats. There's all kinds of stuff that you can do that I recommend. Just play with it. Just get started. And then what I want to tell you that's really cool, which I think is going to change the game, is your mom can do this too. If you click down. Because all of Apple iMessages are also using post-quantum. So you don't have to be the only one playing with post-quantum algorithms. Because it's being embedded for a larger consumer population, I think this is going to be the single most impactful thing. Hey, don't get me wrong. In lockdown mode, you still can't use iMessage, right? So there's still issues of other vulnerabilities and other problems and ODAs and backdoors and all the things. There's still issues. However, what I'm suggesting is that for the wider security, having post-quantum already embedded into something that is a consumer application is the long-term best approach. So if we go to the next slide. So I wanted to close by saying it is going to take us a while. We're not going to be done in the 10-year horizon that we need to finish stuff in or yesterday. So I think the clue is iterate and improve every time. Build in that crypto agility. Make sure that you have your org with you because this might cost money. This will cost money. Not might, it will. And find out who it is you can trust for this evaluation as time goes on. So you do need to talk to your National Cybersecurity Center or NUKIP or whomever. And there are 2 reports that I helped write with the World Economic Forum. One is the transition to a quantum secure economy, and the other one is this building a quantum economy. One is more on what's the state of quantum, and the other one is more on how do we transition effectively with everybody. So check those out. Start now. I realize that quantum is not the biggest priority if you are underneath the information security poverty line and cannot fix vulns and don't have any clue what your assets are. Do that first, but then prioritize the things that are important before they become urgent. Thank you.